In this video, I'll be looking at a slightly more complicated circuit than the ones we've been looking at so far. We'll do the analysis of it, and you might find out that the algebra to analyse even comparatively simple circuits can rapidly get out of hand. This is the circuit we'll be looking at. 2 resistors and 2 capacitors. Now, while the full expression for the frequency response of this circuit is a little bit complicated, as you can see at the bottom there, we can derive some asymptotic cases, a low frequency approximation and a high frequency approximation without too much trouble. And that can be done as follows. If we first consider very low frequencies, well, the lowest frequency we can consider is 0, DC. At DC, the impedance of a capacitor is infinite, because the complex impedance of a capacitor is 1 over j omega c. When omega is 0, that just becomes infinite. So at DC, we've effectively got this circuit. An alternating voltage there, going through a resistor. The capacitor is effectively not there, it's an infinite impedance. That goes through another resistor R2 here, and another capacitor, which is effectively an infinite resistance. So that is the, well, I'm not going to call it a circuit because it's not a circuit. There's nowhere for the current to flow round. And if there's no current flowing round, then there's no potential difference across any of these resistors. If there's no potential difference across resistor R1, then the output voltage at this point here must be the same as the input voltage at this point here. And that means that the amplitude response is going to be 1. H of omega is just 1. Now, at very high frequencies, things are a little bit more complicated, because we can't often assume that omega is just infinity and then the capacitors have a complex impedance of 0. If we did that, we would end up with this circuit here. R1 still has the complex impedance of R1. Capacitor C1 has a impedance of 0 at infinite frequency, which means that it's effectively just behaving like an ideal wire. R2 would have still its impedance of R2, and C2 would behave like a wire. We would have that circuit. At this point here, my output is now directly connected to ground through C1, therefore Vout is 0. That's not a terribly useful high-frequency approximation. So I have to do a bit more thinking to work out a reasonable high-frequency approximation. And I might proceed like this. First of all, consider that the capacitors are not 0 impedance, but just a very small impedance. If I write this as Z2 for the time being, it's the complex impedance of capacitor 2, and this as Z1, complex impedance of capacitor C1, then I could note that for these 2 components here, these components are in series. You work out the total impedance of 2 components in series by adding up the impedances of the 2 components. So the total impedance of this part of the network here, R2 plus Z2, is approximately equal to, well, if Z2 is tiny, very, very small, then R2 plus Z2 will be approximately equal to R2. So I can do my first approximation, high-frequency approximation of the circuit, and it would look like this. R1, that capacitor is still there, but these 2 components have been replaced just by the resistor R2. Next, consider these 2 components here in parallel. That's a capacitor with a very small impedance at high frequencies in parallel with a resistor, which just has its frequency independent value. Now, for 2 components in parallel, the total impedance is the product of the two impedances divided by the sum of the two impedances. If Z1 is tiny, then R2 plus Z1 is just going to be approximately equal to R2. I can neglect that plus Z1, in other words. Well, having done that approximation, I can eliminate R2 in this equation and derive that the total impedance of this parallel network here is just equal to the impedance of this capacitor. So I can approximate my circuit at high frequencies as just R1 and C1. And we know how to analyse that one because we've done it before. It ends up with a frequency response of approximately minus j over omega R1 C1, which I've written previously as e to the j minus 90 degrees or minus pi over 2 over omega resistance times capacitance, but it's the same thing. Working out the complete frequency response, however, is a bit more of a faff. We would have to consider R2 plus the complex impedance of C2, which is j omega C2. That's the sum of these two impedances. These are in parallel with this capacitor C1. So if I wanted to know what the total complex impedance of these three components here is, C1, C2 and R2, it would be this multiplied by the complex impedance of C1 divided by 1 over j omega C1 plus R2 plus 1 over j omega C2. And what I've done there is just use the rule Z equals Z1 plus Z2 for two series impedances. And having got the impedance of these two components, R2 and C2, just used the formula for the impedance of two components in parallel and taken the impedance of C1 and the impedance of these two components in series and put them into this formula and ended up with this. I've now got a potential divider, a circuit that has a voltage input here, goes through a resistance R1 into an impedance Z given by this expression here. I can now use the potential divider formula, and that would tell me that the frequency response, which is V out over V in, is this expression here. I'll call this, I'll just call this Z, Z over Z plus R1. And now I just have to do a simplification job. Well, the first thing I will do is look at Z and multiply top and bottom by j omega C1 times j omega C2. That would give me on the top 1 plus j omega C2 R2, and on the bottom j omega C2 plus j omega C1 plus R2 times j omega C1 j omega C2. And if I now put this expression for Z into this formula here, I'll get the frequency response as 1 plus j omega C2 R2 over this lot. Won't bother to write it out. Over 1 plus j omega C2 R2 over this lot plus R1. If I define this lot as just the denominator here as D, I could write this as this perhaps, where D is the sum of these three terms. Right, multiply top and bottom by D, and I end up with 1 plus j omega C2R2 over 1 plus j omega C2R2 plus R1 times D. This is D. That would give me j omega R1 C2 plus j omega R1 C1 plus j omega squared times R1 R2 C1 C2. Now, j omega squared is j squared times omega squared. Well, j squared is minus 1. So this term here just becomes minus omega squared, R1, R2, C1, C2. These terms here all have a common factor of j omega, which I could extract, and that would allow me to write my final result as 1 plus j omega R2 C2 over 1 plus j omega R1 C1, that's this term, plus R1 C2, that's from this term, plus R2 C2, that's from this term, minus omega squared R1, R2, C1, C2. And that's my final expression for my frequency response. Fit on the page. Just about. But this is a comparatively simple circuit. Just 2 resistors and 2 capacitors. They get rather nastier, which is why we tend to use simulation to determine their phase and amplitude responses at different frequencies, rather than hack through all of this algebra, unless we really can't avoid it. I've put in some sample values for the resistors and capacitors into this network, so you can see what the shape of this response actually ends up looking like. And you'll see that at very high frequencies, it does have a 20 dB per decade slope, going from 100 kilohertz to 10 kilohertz here. The gain has decreased by 20 dB, but it doesn't have a smooth transition anymore. There's this kind of bump in it. For interest's sake, these component values are not arbitrary. This is what they call a Riaa filter. It's a filter used in the recording industry to balance out the high frequencies and low frequencies when you're pressing recordings onto a vinyl record in order to play them. There will be lots more examples of circuits to analyse in this form coming up, but for now, that's all I want to say about the topic.